Welcome back to ECE 501B. Thank you for watching and listening. Today I want to remind you that homework number 3 is due on Monday the 26th. Exam number 1 is the following Wednesday the 28th. So please start to get ready for that exam. If you haven't already, you should be able to find review material on the D2L website for exam number 1. We'll quickly go through, as a part of our goals today, the exam number 1 process and the structure of exam number 1. Again, you'll see examples of what exam number 1 looks like on the website, and what I'm really wanting to do is focus on finishing up our time in chapter 3. We'll talk about really two main linear maps, an operator T, which takes from an input vector space and maps back into that same vector space as the output vector space. We'll talk about linear functionals, which is another linear map that goes from a vector space, an input vector space, into the field of numbers, which is one-dimensional, that the vector space is living on or using for its scalars and elements. We probably won't say much about products and quotients at this time. That's section 3E. And if we need to get those product spaces and quotient spaces, then we'll come back to that section in chapter 3 at a later date. But what we will do in section F of chapter 3 is talk about these linear functionals. It's a linear map from a vector space into, let's say, the real line or into the complex numbers, but it goes from the vector space V into F, and typically for us that will be the reals. We will then conclude the material in chapter 3 that we will be focusing on right now by talking about some of the common properties of matrices, the transpose, what happens when we transpose a product, and we'll talk about rank, column rank, row rank, what the generic rank of a matrix is. It's the column rank or it's the row rank. They're all going to be the same. And we may talk a little bit about dimensions, but maybe not. Then we will quickly summarize the main points from chapter 4. This list is getting longer and longer for our goals, and we will then try to motivate what we will be talking about in chapter 5, which is this new concept dealing with maps, and in particular restrictive maps, which are these operators that take a vector from the input vector space and map it back into the same vector space. When we have operators, we can talk about eigenvalues and eigenvectors, and we'll try to get a little bit of a background feel for that in terms of these invariant subspaces. As a reminder then, for exam number 1, you are able to bring 2 sheets of notes that are the standard 8.5 by 11, and you can fill both the front and the back of those 2 sheets. You can bring a calculator and something to write with, but that's really it. I don't want you bringing a textbook or class notes. You're not going to be talking on your cell phone or using your cell phone. No computer and no classmates, no help. The structure of exam 1, there will be 5 problems. One of those will be a proof, and you may have to demonstrate or show or produce counterexamples from some other problems, and you may have to create or build something using definitions, propositions, these ideas of vector spaces, subspaces, direct sum, basis, matrices, what it means to be an injective map or surjective map, and how those then relate to null space and range space, and whether we have things spanning a range space or spanning a particular set of vectors in the input space or the output space. So let's talk a little bit then about two of these different kinds of linear maps, and the first one that we will talk about is an operator. And an operator is a specialized linear map, and it's a linear map that takes a input vector space, and this linear map maps back into the same vector space V that we started in, or that was the input vector space. It also is the output vector space. And we may refer to the set of all operators on this vector space V. We may shorten the notation. Instead of saying the linear maps from V to V, we may just collapse that and say the linear maps on V, which is now then these operators T live in this vector space of linear maps V to V. And the reason that we're concerned about operators is because they make up the majority of the remainder of the class. Let's start then with these operators by showing some of the specialized results that happen when we do deal with operators. And that is now this equivalence between injectivity and surjectivity when we're dealing with operators on finite dimensions, or linear maps on finite dimensions, which these linear maps are specialized to be operators. So let's now, this is Theorem 69 from Chapter 3, which says that injectivity is the same as surjectivity. If you have a operator that has a trivial null space, then it's going to have a onto mapping, or a surjective map, which is going to then cover the entire output vector space, which is also the input vector space. Or if V is a finite dimensional vector space with a linear map T, which is now a linear operator, we can then show that the following statements are equivalent, or that they apply each other. The following statements imply each other. Statement 1 is that T, the linear map, is invertible. Statement 2, T is injective, which means it has a trivial null space. And 3, T is surjective, which means that the range of T is the entire output vector space, which, when we're dealing with operators, that's the input vector space as well. Let's look at showing these implications, or a proof. So first, let's assume that we have a linear map that satisfies statement 1, or that is invertible. Then 2, the map is injective, is implied by the definition of invertibility. Where that's, if we remember where our propositions or theorems are, that one actually follows from proposition 56 in chapter 3. So if we assume that our map is invertible, then T is injective, or we have a trivial null space. Or we've now just concluded that statement 1 implies statement 2. Now we're just going to sort of string these together. Let's now assume that statement 2 is true. If statement 2 is true, that we have an injective map, then we know that the null space of that linear map is trivial, or it's the zero vector, then we can look at a previous theorem, and that previous theorem is in fact Theorem 22, which says that the dimension of our input vector space V is equal to the dimension of the null space of T. Let me go ahead and write that out. Plus the dimension of the range of T. But if we know that the null space of T is trivial, now we know that the dimension of V is equal to 0 plus the dimension of the range of T, and since we have 0 adding to something, we now can say that the dimension of the range of T is the same as the dimension of our output vector space, which is the input vector space. Or now we can reach all of our output vector space, which says that T is surjective. And we now have been able to conclude that if we start with statement 2, that implies statement 3. And if we assume the last statement, statement 3, that our linear map T is surjective, that means then that the range of T is equal to our output vector space, or which is the input vector space. And again, if we look at Theorem 322, which gives us this relationship on the dimensions of various subspaces, the dimension of V, which is the size of our input vector space, is equal to the dimension of the null space of T plus the dimension of the range of T. But we just now have stated in statement 3 that the range of T is in fact equal to V, so that this dimension of the range of T is the dimension of V. That allows us then to conclude that this null space of T has dimension 0, which means that to have 0 dimension, we need it to be the 0 vector. And so our null space is the 0 vector, which says that the map is injective if we've now started with the map being surjective. We assumed that it was surjective in this part of the proof. So T is surjective. That was assumed here. We've just shown with that assumption that we can conclude that the map is injective. And once we have a map that is surjective and injective, then from proposition 356, the linear map is invertible. And now we've been able to go full circle. We showed that 1 implied 2, 2 implied 3, 3 implied 1, and we can now get from any of those statements to the others, so that now each of these statements implies the other. If we now look at another, that was what we can look at when we're dealing with an operator. That's a linear map from an input vector space back into it itself. Let's now define another linear map, and in particular this is coming to us from definition 92 in chapter 3, which is the definition of a linear functional. here a linear functional on an input vector space V is a linear map from the input vector space V to our field of numbers F. Let's just illustrate this with some examples. It's probably better to start thinking about examples rather than try to get our head around what this means, a linear map from the vector space to the reals or complex numbers. The notation that we will use for these functionals is phi, and let's just start with a phi that's operating on a vector space R3, where so we have three-dimensional space x, y, z. We need to now find a function phi that will map into the reals. And one way to do that, if x and y and z are real, we could just do some linear combination of those. Suppose it's 5x minus 4y plus 2z. Now we start with this 3 vector x, y, z, and it gets mapped into a scalar, which is our field of numbers. So this is now our linear functional, or one example of a linear functional. Another example is, suppose that we now have our input vector space is Rn or Fn. Let's now pick a particular vector in that same vector space Fn, and that's now fixed. Let's now define a linear functional phi that will map from Fn to F. And one phi to do that, if we now start with a generic vector in Fn, which is now having coordinates x1 through x sub n, let's define that. Now we'll use this fixed vector that we decided on, C1 through C1, and we'll use each of those scalars to scale the coordinates in this arbitrary vector x. So we have C1, x1, C2, x2, etc. up to C sub n, xn. We sum all of those up. Each of those products is just going to be a scalar, and we sum up those scalars and we'll get a scalar. So we start with an n vector, and for a fixed C1 or C vector, C1 through Cn, we'll generate a scalar. And this is sort of one way of thinking about or foreshadowing what we will be doing when we talk about an inner product. You might, but there an inner product typically has two vectors, x and y. Here one of those vectors is fixed. But you can now think of an inner product as one way to create a linear functional. But this inner product will have a fixed vector C1 through C sub n. Another example of a linear functional, let's say that now our vector space is the set of polynomials over the reals, and we now want to map that. It's over the reals, so we need to take it back into the reals. One way to do that, we could now take any polynomial p and say, why don't we take the second derivative of p, evaluate that at x equal to 5, and scale it by 2. That produces a scalar, and we could even make that a little bit more complex. We could say plus 6 times that same polynomial evaluated at 1. So now we might look at a linear combination of the second derivative of that polynomial evaluated at 5 plus that polynomial undifferentiated evaluated at 1. And that may mean something to us, but it does provide us with a number that's real, and we started with any general or generic polynomial in the vector space of polynomials over the reals. If we're dealing with polynomials, another linear functional, let's say again that we're dealing with polynomials over the real, and to be a linear functional it needs to map back to the reals. We can produce a real number by simply integrating a definite integral, let's say from 0 to 1, of that polynomial with respect to x and evaluating at 0 and 1. Now that we have linear functionals defined, they are simply linear maps from the input vector space to the field of numbers. We can actually define what's called a dual space. If we start with a vector space V, then we will call its dual space, let's say V prime, where the dual space of our input vector space, or a vector space V, which we are labeling or denoting V prime, is the vector space of all linear functionals on V. That is, V prime is really this set of linear maps from V onto F. That's V prime. That's our dual space. It's this vector space of all linear functionals on V. One more comment on these dual spaces before we move into some matrix properties, and that's provided to us by Theorem 95 in Chapter 3, which says that the dimension of the dual space is actually equal to the dimension of the input vector space V. That's sort of the heading that they give to this theorem, where this theorem says that suppose that V is finite dimensional, then the dual space V prime is also finite dimensional, and its dimension, the dimension of the dual space, equals the dimension of the input vector space. To show that, really all we have to do is return to a previous result, or we might just say something like follows from Theorem 61 in Chapter 3, but if we remind ourselves of what that theorem was, that theorem gave us a result concerning dimensions of these linear maps, where the dimension of the linear map from V to W, and now you might think of some linear map as a matrix even, that's maybe m by n or 3 by 2, we know that the dimension of that vector space is now the dimension of the input vector space times the dimension of the output vector space. And we want to find in this particular theorem if the dimension of V prime is equal to the dimension of V. Well, if we look at the dimension of V prime, that's just the dimension of the linear map from V to F. But from Theorem 361, we just know that the dimension of the linear map is the dimension of V times the dimension of F, the output vector space, And we know that this dimension is 1, so that now we can conclude that the dimension of V prime is in fact equal to the dimension of V. So there are some points on operators, linear functionals, and dual spaces. Let's now finish up chapter 3 by talking about some remaining matrix properties that I want you to be comfortable with. First is the fact, or this concept of the transpose of a matrix. And I may just sort of list these. This says then that the kjth element in the transpose of a matrix A is equal to the jkth element in that original matrix A. Another property that I want you to be able to use is the transpose of a matrix product. And for the demonstration of this, you can look at the book, but here if we have the matrix product AC and we want to look at its transpose, that's equivalent to C transposed times A transposed. And the last thing that we will talk about is rank relative to matrices, and we'll introduce some definitions first. First is that the row rank of a matrix, let's say A, the row rank of A is actually equal to the dimension of the span of the rows of the A matrix. And we can also talk about the column rank of a matrix. The column rank of A is the dimension of the span of the columns of A. With those definitions, we can now introduce some propositions. Proposition 117 says that the dimension of the range of T actually equals the column rank of the matrix of this linear map T. So if we want to know the dimension of the range space, we just need to look at, or we can look at, the matrix associated with the matrix representation of the linear map T and find its column rank. And hopefully you can remember or get up to speed on how to find the column rank. A lot of times you'll transpose the matrix and do row reduction, and then that will give you the column rank. The row rank, the reason you can do that is because proposition 3.118 says that the row rank equals the column rank of a matrix. And if that's the case, then we might as well just start talking about the rank of a matrix since it's all the same. And that's what definition 319 deals with, which is the rank. And that says that the rank of a matrix, let's say that matrix is now M by N, that rank of that M by N equals the column rank of A. And those are the points that we want to keep in mind or be able to use to conclude chapter 3. What I want to do now is quickly go over some main points in chapter 4. which is dealing with polynomials, and we will need some of these polynomial facts as we work further into the textbook. Here, let's just remind ourselves of what we have. We could say we have a polynomial p of z that is, let's say, a sub 0 plus a1z plus a sub 2z squared. The subscripts of our coefficients, which are in our field of numbers, match the power of z. Then we have a sub m z to the m, and that's now living in this set of polynomials over the field f, where f could be either the reals or complex. We can now talk about roots of those polynomials. And in particular, if we look at proposition 10 in chapter 4, that now in terms of its heading says that each zero of a polynomial corresponds to a degree 1 factor. Writing that out then a little bit more symbolically, suppose that we now have this scalar lambda in our field. That scalar lambda is a root of our polynomial p of z. If and only if we can factor p of z into the product of a linear factor z minus lambda times a new polynomial p of z, or we can factor out that linear factor from p of z. And it's important to realize that what we're talking about with respect to roots, that depends on what field we are working on or living on. So the roots depend on whether f is real or f is complex. Theorem 13 in chapter 4 is concerned with the fundamental theorem of algebra. And here we are actually assuming that our field of numbers is complex. This theorem now, the fundamental theorem of algebra, now says that every non-constant, and that's important, we need these polynomials to not be just a constant, every non-constant polynomial with complex coefficients has a root. So you give me a first order, a 10th order polynomial, it's going to have a root. It has to be non-constant. Once we have that, then we can talk about factoring that, which is Theorem 17, which says this is the factorization of a polynomial. And here let's now say that we're factoring over the set of real numbers. Our scalars then are real, and all of our other parameters, the c, which is a constant, lambda 1, lambda 2, lambda sub m, those are all living or are real scalars. The alphas and betas are also real coefficients, and we are now assuming that alpha sub I squared, or the alphas and betas, are related in such a way that alpha sub I squared is less than 4 beta sub I. If we now have that relationship that our lambdas and c are real, alphas and betas are real, with this particular relationship between alpha and beta, then we can factor these polynomials, any generic polynomial that is over the field of real numbers. Real and quadratic factors of a polynomial can be identified. Meaning we now can look at p of x as some constant times x minus lambda 1, x minus lambda 2. Remember, these lambdas up to lambda sub m are real. And then we end up with quadratic factors that cannot be factored into linear terms, and we can keep going up to x squared plus alpha sub m x plus beta sub m. Meaning those quadratics, that's as small as we can collapse that down. We cannot identify real values for lambda that will satisfy those quadratics. Where now, just remind ourselves of the quadratic formula as to why it is that we can't factor those last capital M factors that are quadratic. Quadratic formula says that if you are given x squared plus alpha sub I x plus beta sub I, then we can use the quadratic formula to find the roots, where the roots are now minus alpha sub I plus and minus the square root of beta sub I squared minus 4a, which is 1, times beta sub I over 2 times a. Well, if we look at that formula, when do we end up with complex values for x or for roots? It depends on this discriminant. Whoops, I needed to be reminded that this is now the b, which is in this case the alpha sub I. So this is alpha sub I squared minus 4 beta sub I, and we call that argument of the radical alpha sub I squared minus 4 beta sub I. That's our discriminant. And when that is less than 0, or when alpha sub I squared is less than 4 beta sub I, which is what we said is the case on these capital M factors, quadratic factors, when that's the case, that discriminant, when it's negative, that gives rise to imaginary roots. That's why we said that we cannot find real roots that will allow those quadratic factors to vanish. We needed to introduce, or we would have to introduce, complex numbers in order to obtain roots for those quadratic factors. And those are the key points from chapter 4 that we want to remember, that every 0 of a polynomial corresponds to a degree 1 factor. Every non-constant polynomial with complex coefficients has a root, and we can factor a generic polynomial over the field of reals as made up of linear factors and complex or quadratic factors. That now allows us to move into Chapter 5, which is dealing with eigenvalues and eigenvectors. Remember, what we said we were going to be doing for the remainder of the course is probably working with operators, which means that our input vector space is equal to our output vector space, or these linear maps are taking a vector from the input vector space and mapping back into that same vector space. And if we looked at these maps, or the matrix representation of these maps, we're now going from n back into a dimension n over this field F. A now, this matrix representation, is a square matrix. And what we want to do now is talk motivationally about eigenvalues and eigenvectors. Here's our concept. Excuse me. We have the matrix representation of a linear operator, which is a square matrix A, and the elements of that matrix are coming to us from our field of numbers F. This, what I'm writing down now, is actually going to be the eigenvalue eigenvector equation, which says that we take this square matrix, which is the is the matrix representation of the linear map. We operate on a vector x, and that now produces a scaled version of that same x, where this scalar, lambda, belongs to or is an element of our field of numbers, and these vectors, which it's the same vector x on the left side and the right side, this is a vector with its elements or coordinates in the same field F. We now have a linear map from an input vector space to an output vector space that's the same. So we're a linear map from V to V. If we looked at the matrix representation of that linear map, it would be a square matrix A. And if we can find a vector x and a scalar lambda that satisfies this equation, then we will give particular descriptors to that scalar lambda and the vector x. In this equation, if x and lambda exist, then x is an eigenvector, and lambda is an eigenvalue. And what this says, so you'll want to really commit this to memory. Ax equal lambda x. So square matrix times a vector is now going to produce a scaled version of that vector x. The operator, this square matrix A, takes a vector, which we were calling x, and maps back into a scaled version of that same vector, a scaled version of that same vector. And that vector is our eigenvector, and the scaling is the lambda. And that scaling is, or belongs to, our field of numbers F. Suppose that let's look at sort of an example of this, or try to get an image of what we're working with. Suppose that X, our eigenvector, is coming to us in or out of R3. So some three-dimensional vector, or some vector in 3D space. If that vector X is an eigenvector, which means that it needs to satisfy that eigenvalue-eigenvector relationship, AX equal lambda X. X is such a vector. If X is an eigenvector, then the operator's action, the A matrix, keeps the point, which is the end of that vector X in three-dimensional space, keeps the point in 3D space on the same line as it started on. So even though we might have much more interesting mapping from this matrix A, it actually takes us right back on, or keeps us on, the vector that we started on, which is our vector X, or our eigenvector. Let's look at some examples of matrices and corresponding eigenvalues and eigenvectors. Suppose, and let's keep it somewhat manageable, let's start with a 2 by 2. These A matrices have to be square, since we're mapping from a vector space back into itself. In this case, let's make note of what we have with A sub 1. A1 is a diagonal matrix which is very special, or it's a nice matrix operator. So now with this A1, let's suppose that we sort of know what we're anticipating, or what we're doing. Suppose that V1, a vector, this is now the X that we've been calling before, but now V1 is an X. Suppose V1 lies on the X-axis. And let's just pick a convenient vector that lives on the X-axis, or sort of, you could think of it as a standard basis vector. What happens when we operate on that vector with this diagonal matrix A sub 1? We have A1, V1, but A1 was minus 1, 0, 0, minus 2. But remember what we said we could do with matrix vector multiplication? That vector now is just weighting columns in the matrix that's on its left. In this case, it's simply weighting the first column of A with 1 and weighting the second column with 0. Or now the output is minus 1, 0. That's the result of this matrix vector multiplication. This is our output. And I hope that you can see that that output is actually minus 1 times our original vector v1, or we now can say that this is minus 1 times v1. And that's what we were wanting for our eigenvalue eigenvector equation. We wanted to have a matrix times a vector giving us the same vector just scaled, where this resulting output vector actually remains or stays on the x-axis. And the output is scaled by minus 1 from the input. So that's what happens with v1. Let's look at a different vector. Suppose we take another vector. Again, we're still keeping the same matrix A1, which was diagonal, with minus 1, minus 2 on the diagonal. Suppose v sub 2 lies on the y-axis. We picked a nice vector for v1. We might as well pick a nice vector for v sub 2 and the y-axis, and that's just 0, 1. Now if we look at a1 v2, this is now minus 1, 0, 0, minus 2 times 0, 1. Hopefully now you're getting the hang of these matrix vector products. This is just pulling off the second column of A1, which is 0, minus 2, but that's now a scaled version of this vector v sub 2 that we started with in terms of multiplying it by A1. Meaning now the output vector, which is this guy, is in fact a scaled version of where we started, or the output vector stays on the y-axis. And it's actually scaled by a real number of minus 2. And we can make some comments relative to this example of this 2 by 2 matrix that's diagonal. One is that the initial vectors that we selected, v1 and v2, were actually eigenvectors because they both ended up solving that eigenvalue eigenvector equation. So now our initial vectors were eigenvectors. The scaling quantities were eigenvalues. And now let's just remind ourselves of what we had. We had A1, our 2 by 2 matrix. It was of dimension little n equal to 2. And with that, we found that we had two eigenvalues. The scalings were minus 1 and minus 2. Those are actually our eigenvalues. We had two eigenvectors. Again, our dimension, or A1, had 2 rows and 2 columns. That 2 is special, saying we have two eigenvalues, two eigenvectors. The scaling values were real. And finally, this A1 was diagonal. And if we remember what our scalings were, they were exactly the numbers that were on the diagonal. The eigenvalues were the diagonal elements. Let's look at another example. Example 2, we'll say A sub 2. In this case, let's let our A matrix, let's say that we mix it up a little bit. Before it was diagonal, let's go ahead and put some value in the upper, or in the 1, 2 entry of our A matrix to make this matrix A sub 2 upper triangular. Now, triangular matrices, upper or lower, still allow us to end up with some easy or easier properties or characteristics. One is that the eigenvalues of this upper triangular matrix are in fact -1 and -2. Those eigenvalues are still on the diagonal. And lambda 1 is -1, has an eigenvector v1 that's the x-axis, and lambda sub 2, which is -2, has an eigenvector v sub 2, which is in fact -1, 1. And we can try to verify that. We want to see what the matrix vector product A sub 2 V sub 2 is equal to. We have A sub 2 was -1, 1 in the top row and 0, -2 in the bottom row. We want to multiply that by V sub 2, which is -1, 1. Well, that now says we want to scale the first column with -1 and add to that the second column scaled by 1, or we now have 2 times -2 for the output vector. But in fact, if we factor out a -2 from that 2 -2 output vector, we end up with -1, 1, and lo and behold, that's the same as V sub 2, which is what we started with. So this vector V sub 2 does allow us to write down or satisfy this eigenvalue-eigenvector relationship. So when we have diagonal matrices or upper or lower triangular matrices, we can immediately find the eigenvalues, and finding the eigenvectors is not too difficult. But let's now show, maybe with this next example, how we might be able to find these eigenvalues and eigenvectors that maybe aren't jumping out at us or screaming at us from the matrix representation. Suppose we start with a matrix B whose first row is -3 halves, -1/4. So we're not changing up much in terms of dimension. We're not changing the dimension at all. It's still 2 by 2. And let's say the last row is -1, -3 halves. This particular matrix is obviously not diagonal. It's not upper or lower triangular. It's actually quite dense in terms of a matrix. It has a non-zero value in every one of the four elements of B. What we want to look at is, does this B actually have any eigenvalues that are real? Does B have any real eigenvalues? And if it does, is it possible to compute those eigenvalues? Now, if it does, then we need to find real values for lambda that satisfy this equation. Bx is equal to lambda x. And if we don't know, if we can't see right away, which we may not be able to, what that vector x needs to be, we know it has two coordinates. Let's just call those coordinates x1 and x2. And if we put that parameterized vector in to this eigenvalue eigenvector relationship, then we end up with minus 3/2 minus 1/4 minus 1 minus 3/2 times x1, x2. We want that to equal lambda, some real lambda, times x1, x2. Let's now just create these equations that relationship now implies. If we look at the top row, we have minus 3/2 x1 minus 1/4 x sub 2. That's equal to lambda x1. The second row says we have minus x1 minus 3/2 x2 is equal to lambda x sub 2. Let's now combine the terms that share the same x's, meaning if we subtract lambda x1 in the top equation from both sides, we have minus 3/2 minus lambda times x1 minus 1/4 x sub 2 is equal to 0. Let's call that equation A. And the second equation now says we have minus x1 plus minus 3/2 minus lambda x sub 2 equaling 0, and that's equation B. Well, from B, we can solve that for x1. x1 is now minus 3/2 minus lambda x sub 2. Let's now take this expression for x sub 1 and put it into equation A. Or let's substitute the equation that we have from equation B into equation A. And doing that, we now have minus 3/2 minus lambda times minus 3/2 minus lambda x sub 2 minus 1/4 x sub 2 is equal to 0. And what we want is that for that to be true for any value of x sub 2. Therefore, if we look at that, we have minus 3/2 minus lambda squared minus 1/4 times x sub 2 is equal to 0. And we want a non-trivial solution. We don't want x sub 2 to equal 0. So is there a real lambda, or is there a lambda that is a real number that allows that square bracketed coefficient scaling x sub 2 to equal 0. And if we look at that, that's really just a quadratic in terms of lambda. We now can see that minus 3/2 minus lambda squared needs to equal 1/4 by setting that square bracketed term equal to 0, or that coefficient of x sub 2. If we look at this, then, or if we take the square root of both sides, we now have minus 3/2 minus lambda equaling, and if we take the square root of 1/4, we actually need plus and minus 1/2. And now we have some equations that contain one variable lambda. We can isolate that lambda. Lambda now is minus 3/2 minus plus 1/2. Or we have minus 3/2 plus 1/2, which is now minus 1. And we have minus 3/2 minus 1/2, which is minus 2. And lo and behold, those are both real, and they both are equal to the same eigenvalues that we had for A1 and A sub 2, those earlier matrices. And these are definitely not the same matrix. B is not the same matrix as A1 or A2. But we've now found values of lambda that satisfy that eigenvalue-eigenvector relationship. Let's see if we can now find the eigenvectors associated with those eigenvalues, minus 1 and minus 2. And we can find that if we return to one of the equations, or the set of equations, we have minus 3/2 minus lambda times x1 minus 1/4 times x sub 2 equaling 0, and minus x plus minus 3/2 minus lambda x sub 2 equaling 0. And that's sort of begging for us to put that into a matrix. We now have minus 3/2 minus lambda. That's going to be scaled by x1. X sub 2 is scaled by minus 1/4. We have minus 1 times x1 in the second equation, and minus 3/2 minus lambda times x sub 2, and those now equal the 0 vector. If we can find an x1 and an x2, some combination of coordinates in our x vector that gives us the 0 vector, then we're in good shape. But what do we see? Well, this is really our original matrix B minus lambda I, and this x vector, if it, when multiplied by b minus lambda I, gives us the 0 vector, then that x vector is in the null space of this matrix b minus lambda sub I, or another way of writing that is x, this vector, is in the null space of b minus lambda I. And we have now two different values for lambda that we want to see if we can obtain two different eigenvectors, x sub 1 and x sub 2. So x1 and x sub 2, two different sets of that. Let's look at one of our eigenvalues, which was minus 1. When lambda is lambda 1 of minus 1, we can now replace lambda with minus 1, so we're now adding 1 to both of those diagonal entries, or we now have minus 1/2 minus 1/4 minus 1 and minus 1/2 times x1, x2 is equal to 0. Now, if you look at this, maybe it won't take you too much, but hopefully you see that these columns are just a scalar multiple of one another. Or if we multiply the first column by 1/2, we end up with the second column, meaning these columns are dependent on each other. And that's really what's going to happen when we found the eigenvalues that work in that eigenvalue-eigenvector relationship. Since those columns are dependent, now we know that the null space of that matrix B minus lambda sub I is going to have non-zero values in the null space, or we will have a non-trivial null space. So we need to find values or some linear combination of x1 and x2 that make this happen. We can do that by simply allowing one of those two variables to be some number. Let's just pick an easy number. Let's let x1 equal to 1. Now in the top, or let's just use the bottom row since it looks like it's easier to work with numerically. We have minus 1 times 1, or minus 1 times x1, which is minus 1, minus 1/2 x sub 2 is equal to 0. We've already picked one of our two unknowns when we've set x sub 1 equal to 1. If we now solve this for x sub 2, we get x sub 2 x sub 2 is minus, or 1/2 x sub 2 is equal to minus 1, or x sub 2 is equal to minus 2. We'll solve that. So that now we've found that one of our vectors associated with lambda 1 equal to minus 1 is our eigenvector. So now we have an eigenvalue of minus 1 with an eigenvector of 1 minus 2. If you plug in lambda sub 2 equal to 2 into the same relationship, you will find that that also has a solution. If we let x sub 1 equal to 1 again, this will now be 1, 2, and we can see that those two eigenvectors are different, which is a good thing. Our eigenvalues are different, and these are now the directions which, if we operate on with this operator A, we will stay on those vectors, and they will just be scaled versions after going through the map A. I think I want to then stop with that, but these are now the eigenvectors. For the appropriate eigenvalues, lambda 1 equal to minus 1 and lambda sub 2 equal to minus 2, we've still found that we have real eigenvalues for that B. Are there actually matrices that have real elements in them that maybe do not have real eigenvalues? And I think we'll start with something like that in our next time that we meet.